Here we have the infinite series of 1 dividing by 5 plus the square root of n. And we want to use the direct comparison test or the basic comparison test to show that this series right here diverges. Now the direct comparison test, it says that if we want to show this series right here diverges, and then we need to come up with a series B sub n. So we'll call this right here A sub n. So this is A sub n. We have to come up with a B sub n and then show that the series B sub n is less than the series A sub n, and show that the series B sub n diverges to infinity. So basically what we're trying to show is that if this goes to infinity, then the series A sub n is larger than infinity, which means that it's equal to infinity and it diverges. And so that's the strategy. And then in the previous examples, if we normally would just drop the constant, if we drop the constant, then we just get 1 divided by the square root of n. So 5 plus the square root of n is greater than the square root of n. Therefore 1 dividing by 5 plus the square root of n is less than the square root of n. So this right here, this is less than that. Since this, the denominator of 5 plus the square root of n is larger than the square root of n, if we do the reciprocal, then it'd be less than. And so this means that the series A sub n is less than the series B sub n. But we want to show that this series 1 divided by 5 plus the square root of n diverges. And so we need to show that B sub n is less than A sub n, and this is the other way around. This right here, this is A sub n. And this right here, this is B sub n. And so one more time, to show the divergence, we need to show that B sub n is less than A sub n. And so here we have A sub n is less than B sub n. And so this B sub n right here is not going to work if we want to show that this series right here diverges. And so what we have to do is come up with another B sub n. And so if we let this right here be 1 divided by n. So we let B sub n be 1 over n, and A sub n is still 1 over 5 plus the square root of n. And now let's compare these two sequences right here. So the blue graph is the graph for 1 over x, and the red one is the one for 5 plus the square root of x. This is the line x, this is 8. And so if we look at the graph, we will see that so beginning with 8 on, the red one is going to be above the blue one. So beginning with x, 8 or greater, 1 over 5 plus the square root of x will be greater than 1 over x, or to say it another way, 1 over x would be less than 1 over x is the blue, and 1 over 5 plus the square root of x will be the red. So beginning at x equal to 8 and on, 1 over x will be less than 1 over 5 plus the square root of x. And so in terms of series, then the series 1 over n will be less than or equal to the series 1 over 5 plus the square root of n for n greater than or equal to 8. Now, even though the series starts at 1, but we do not care about the first few terms. What we care about is from 8 on. And so now we have shown that the series b sub n is less than or equal to the series a sub n. So to show that in order for us to show that the series 1 divided by 5 plus the square root of n diverges, we need to show that the square root of b sub n is less than or equal to the square root of n, of a sub n. And also we need to show that the infinite series b sub n diverges. And so right here we've shown the first part. The infinite series b sub n is less than the infinite series a sub n. And now we need to show that the series b sub n diverges before we can say that this series a sub n right here diverges. And so we notice the following. The series b sub n is 1 over n, which is the harmonic series, and is a harmonic series, and therefore we know that it's equal, it diverges to infinity, and so the series b sub n diverges. And so what we have is this: the series b sub n is equal to infinity, less than or equal to the series a sub n. So what this says is that the series a sub n is greater than or equal to infinity. And we know we cannot be greater than infinity. And so that means that the series a sub n must be infinity. And therefore, by the comparison test, we have shown that the series a sub n diverges. And so to review what we just did, we let these b sub n be 1 over n. And then we've shown that the series b sub n is less than or equal to a sub n for n greater than or equal to 8. And again, in doing comparison of series right here, we don't care about the first few terms. In this case, we don't care about the first 7 terms. What we care about is the terms from a to infinity. And so we have shown that the series b sub n is less than or equal to a sub n. And then we also shown that the series b sub n right here is a harmonic series and is equal to infinity, and it diverges. And so we've shown 2 things. Series b sub n is less than a sub n, and we've shown that the series b sub n diverges, and therefore by the direct comparison test, the series a sub n, which is this series right here, that it diverges also.